All right, so welcome to How to Achieve Foam-Free High-Performance Building Enclosures. This course is approved for one continuing education unit, GVCI, AIA HSW, NARI Green, CGP, AIBD, and may be relevant to your state-based design or contractor license. Today I am going to be your moderator. My name is Brett Little, and I am the Executive Director here at the Green Home Institute. The Green Home Institute has been around since 2000, and we're a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. I also have to say a huge thanks to our Platinum Plus sponsor, Anderson Windows. Check them out for all of your new construction and remodeling needs. And also, do you support greener homes? Do you want to help keep these webinars going, get discounts on other events, or discounts on green building certifications and more? Check out our membership today. All right, so today our speaker is Ken Levinson. He's the CFO and Sales Director at 475 High Performance Building Supply. Ken is graduated from Pratt Institute in 1989 and has been a registered architect in New York State since 1993. Ken is a certified Passive House designer, a founding board member of New York Passive House, the National Passive House Alliance, and the North American Passive House Network. Ken is a founding partner at 475 High Performance Building Supply. So we thank you for joining us today, Ken, and with that, take it away.
Great. Excuse me. Thank you, Brett. Very glad to be here and to be with everyone. We just briefly want to say that by way of introduction about our company, 475 High Performance Building Supply, that we like to say it's a place where the blower door is king. We're really focused on airtightness and high performance construction. And as today's seminar may indicate, we're not big fans of spray foam, and we're really looking as a company to find alternative pathways to high performance. We also were looking to Passive House Standard as being part of the solution for our sustainable future. We'll refer to it quite a bit. I'll try not to be too annoying about it. We just find it a useful sort of North Star in terms of very high performance metrics, particularly in terms of the building enclosures. But certainly what we're going to be talking about today and what we deal with as a company is a whole range of building performance, from code compliant to higher performance toward Passive House. We actually started as a company coming out of Passive House Renovations. I'm an architect, like Brett mentioned, and my business partner is also an architect, a Dutch-trained architect, and we were working on these projects, Passive House retrofits, and found that we couldn't find the materials and the building knowledge in the industry that would really get to where we wanted to be. And so we started the company out of this perceived need in the marketplace. And we've built the company as an e-commerce website. Our headquarters is in Brooklyn, New York, but we have warehouses across the continent for local delivery, as well as a growing number of sales representatives. We're really focused on building knowledge resources, which the seminar is part of it. We also have ebooks, we have downloadable DWG drawings, we have a very active building science blog. We encourage you to go and check it out, and if you have questions, please don't hesitate to get in touch. We're working from Maine to Alaska, and really trying to work with all of those who are interested in making higher performance buildings. So today we're going to be looking at foam-free high performance building enclosures, and why foam-free is really the question at hand. And we like to refer back to The Graduate, where Dustin Hoffman characters told by the representative of conventional wisdom that plastics is the future. And certainly plastics is everywhere, and we can't get away from it entirely. But like Dustin Hoffman in the movie, we're questioning the conventional received wisdom where today in high-performance building enclosures, spray foam is often reached for reflexively without really thinking through all the consequences. And so as a company, we are looking to raise those questions and see how we can do better. And really digging into spray foam, we like to say that, you know, we're quite opinionated when it comes to spray foam. We have a blog series called Foam Fails. We've developed a motto that says less is best. We know we can't eliminate it, but we do believe that we can make better performance to almost inversely proportional to the amount we limit it. Of course, we have toxic ingredient issues, the global warming potential, fire acceleration issues. But at the end of the day, and these are all significant issues in one way or another, performance is really where the rubber hits the road. And we'll talk about that a little bit in how we see the performance of foam over time degrading and not living up to all that it's billed to be. So we'll come back to this sort of as we move through the talk. So our job number one is first when folks are looking to do a high performance enclosure that they don't just automatically reach for the spray foam, that they recognize that we have choices. Of course, spray foam is picked oftentimes because it's sold as the one thing that can do everything. It can be your insulation. It can be your air and vapor control. It can connect different aspects. When we say that we're going to look for alternatives, we need to address these aspects of performance. Insulation, we have choices. Air and vapor control layers and connections. And we need to really think about how they're going to come together, and that's what we specialize in as a company working with professionals. And we really see the evidence and that we can actually make enclosures that are more robust and more resilient, more sustainable, and really achieve true high performance by limiting the amount of spray foam insulation. So the question then becomes, well, what do we mean by high performance in looking at an enclosure? And so what we're going to do here in the next 50 minutes or so is look at these different characteristics, look at the building science behind them, the importance, and look at how to actually achieve it on the job site in the design and construction and some of the key aspects of it. So we'll do a little bit of theoretical and very practical too. But to dig into this, the first 4 items here listed are listed in the order of importance in terms of delivering building enclosure. In terms of building enclosure performance, first water control, which everyone gets. Keeping the bulk water out. And the second, though, is air control, which people don't really get oftentimes. The third is vapor control. The fourth is thermal control. Folks often think of thermal control excuse me, just distracted here for a moment, and get thermal control, but they don't realize that air and vapor control are actually more important in high performance. Then we look at the materials need to work well in cold and wet job sites. We need things predictable. We need things under control in terms of cost. We can't be spending a lot of money. We actually want to save money in this and build high performance. And we want greater sustainability. We want things to be green overall. So let's dig into each of these aspects as we go through. Air control again. So the water control folks get, we keep the bulk water out. But air control is a much more elusive thing and what we really specialize on again. And to have air control, we need to essentially create an airtight enclosure. And this is whether it's a big building or a small building. The good thing is that airtightness is something that we can measure very, very directly with very simple tools. And we can tell very directly how leaky or airtight the building enclosure is. We'll come back around to that. Now, when we talk about airtightness, the meaning of airtightness is changing over time. Historically, one might have considered something like 5 ACH50 or even 7 or 9 ACH50 as being an airtight enclosure. ACH50 is air changes per hour at 50 pascals. 50 pascals is basically the equivalent of putting about a 20, 22 mile an hour wind on the building. You're pressurizing or depressurizing the building with the blower door fan. And so you have 5 air changes per hour at that pressure. The codes, fortunately, are moving forward along recognizing the importance of airtightness and are mandating 3 ACH50 now in zones 4 through 8. We'll see how that gets enforced or how widely it's actually adopted. And the building science industry has really felt that the overall airtightness limit for commercial construction was about 1.5 ACH50. And that's where things sort of stood, but now Passive House has come along in the last few years and cut that by more than half to 0.6 ACH50, which is incredibly airtight. It's very much building a drum. And so as we move down this scale towards greater airtightness, the materials we use, how we put things together matter more in terms of achieving the goals and having them long-lasting. As we go towards larger buildings, it's easier to get the 0.6 ACH50, or it's easier to have an airtight building, relatively speaking. In this graph, we see on the left, relatively small, we have the floor area across the bottom. Towards the left, we have relatively small buildings, and we see a large scattering of airtightness results. As the buildings get bigger, the airtightness is generally getting better and better as we see the results going lower and lower. So what happens is then we start to look at per square foot measurement based on the enclosure area, so that you are not getting undue benefit by the surface to volume ratio. And those requirements are also getting tighter over time. We have the 2012 code at 0.4 CFM per square foot, 75 pascals, and then going down to the Army Corps of Engineers at 0.25. The FIAS Plus 2015 standard is at 0.8, and then the Passive House Institute recommended standard for large buildings is at 0.33. One question's come up, what or who is the U.S. Building Science reference in the HCH draft? What we refer to is essentially the Building Science Corporation out of Westford, Mass, that has done a lot of the leadership in terms of the American building science. So they have generally argued for the 1.5 historically, at least over the last number of years. So that's who we hang that label with. Yeah, Building Science Corp, that's it, BSC. So air control. So we can measure it, which is great, but why is it so important? Why is it second only to water control in making this high performance enclosure? Well, it's really because it disproportionately affects the really fundamental aspects of the performance of the building. First and foremost, we have the indoor air quality, the healthiness of the indoor air. And it seems counterintuitive that an airtight enclosure would be a healthier enclosure. But the fact is that if you want to maintain the quality of something, you have to have control of it. And the only way to really have control of air is in an airtight environment. So we make an airtight environment, we have control of the air. Now it takes very little energy, and with very simple purpose, we can maintain a high level of indoor air quality. Of course, you can always open windows and let the breeze blow through, but you're doing that at your discretion. We have control of the air, and we maintain it. We need to have mechanical ventilation, of course. All our buildings today are mechanically ventilated. They're just generally very poorly mechanically ventilated with exhaust-only bath fans and kitchen fans and whatnot. Not distributed, no heat recovery, no filters. So if we can have the control and have a decent ventilation, we can really, with very little energy or effort, have very high quality. Comfort is the second thing. Drafts are just naturally uncomfortable. So by increasing the air tightness, we knock down the comfort. Air transported wetting. When we think about enclosures and wetting of it, oftentimes the conversation turns to vapor barriers, vapor retarders, preventing the vapor from diffusing into the enclosure. And there's no doubt that we need to think about that and we need to deal with it, and we're going to talk about that in a minute. On the right, we have a graph, sort of two classic graphs from the Building Science Corporation that talk about compare the liability of diffusion versus air leakage. Above, we have one piece of sheetrock, 4x8 piece of sheetrock, showing the amount of water that diffuses through that sheetrock over the course of a heating season, or a third of a quart of water. That same piece of sheetrock over the same heating season with a small air leak can carry over 30 quarts of water. So this air transported wetting has geometric sort of increase in liability and wetting of the enclosure. So really is the biggest single liability. Last but not least here, the heat loss, and these aren't really in order of importance, I should say. To different people, these are going to be important at different levels, but heat loss and thermal bypass. Air leakage profoundly affects the energy efficiency of the enclosure. Here's also another graph of the wetting, demonstrating the wetting of the enclosure, sort of exponential difference between without leakage and with leakage. But I want to speak about the thermal bypass of the how air leakage affects insulation. So thermal bypass describes heat loss where you have wind washing of the insulation. And if you have, tests have shown, if you have an equivalently insulated enclosure, one that's airtight versus one that's leaky, you could have almost a 5 times difference in performance. So we're talking about a fundamentally different building. It's the difference, you know, on a cold day, cold spring day, with the wind blowing and wearing a sweater and having a windbreaker over that sweater or not. Without the windbreaker, the sweater is not doing you much good. With the windbreaker, it can really do its job. So that's the fundamentals. So Joe Stebrick from the Building Science Corp says air sealing both sides of the wall is more important than the fluffing of the cavity of the insulation in the cavity. So really fundamental. So what we like to see is we want to surround the insulation in air tightness. If we surround the insulation in air tightness, then it's optimized and working to its full potential. We also like to see the air barrier that's enclosing the insulation and enclosing the interior environment to be prioritized inboard of the insulation, not outboard. In this way, the insulation is keeping the conditioned air in the conditioned space. We see this is one example of continuous, a nice picture of continuity of inboard air barrier. And looking at some of the reasons, so we have keeping the conditioned air within the conditioned space. Inboard is better also because it's better protection against condensation risk. Because we're keeping that warm and humid air inside the conditioned space. It's not getting to the cold surfaces where you can have condensation. It's also nice to keep such important things as the air control layer within a climate-controlled environment, so it's more robust and long-lasting. And also during the testing, if it's inboard of the insulation, it's more readily, you're able to find leaks and make repairs and know that you've got a robust airtight layer at the completion of the job. And lastly, the air control layer can also double as a vapor control layer. And we're talking about in cold and mixed climates here. If we go to the hot and humid climate, it's a different discussion in terms of locate where vapor control should be. But for the moment, we're talking about cold and mixed climates. If there are any specific questions on hot, humid climates, we could, after this, I'd be happy to address them. But it's going to make more issues, take something that's quite complex and make it even more confusing. So here we have prioritizing the inboard air barrier. And what do we mean by that? Really what we'd like to see is 70% of the thermal insulation outboard of the primary air barrier. Now that might be a liquid applied membrane on the outside of sheathing, but then you're putting your continuous insulation outside of that liquid membrane, outside of the sheathing, so that in fact, that air barrier is inboard of the insulation layer again. So we have the continuous air tightness, and we next need to think about the vapor control. And we're going to come around, after we go through these different building science aspects of it, we're going to come around to actual construction and putting the parts and pieces together. Yeah, New Jersey is definitely inboard air barrier priority. Definitely the question is New Jersey is mixed climate. We're in zone 5 technically. What are your thoughts on the interior barrier given this information? Definitely New Jersey, all the way down to North Carolina, really, where we start to think about that. Yeah, at the end, if we can come around to a zone 1 and 2, we'll definitely talk about that. So the vapor control. Interestingly, vapor control is the third most important, right? Water, bulk water, then air control, then vapor control. And I could say that this order of importance of these layers with thermal control being fourth, this also comes from Building Science Corporation, Joe Stebrick and John Straub, in terms of that importance. And vapor control, if air control is hard for folks to understand, vapor control gets really dicey and is tricky to understand. Also, with the air control, what we really focus on in terms of making high performance. So the thing about the importance with vapor control is that, you know, poorly insulated walls, the typical way that buildings were done, they basically would heat themselves dry. They bake themselves dry. You know, an old building, it's a radiator to the world. They're uncomfortable and they're incredibly inefficient, but they will pretty much last, you know, forever in some ways, unless they have bad water damage or something else going on. But through the fact that their inefficiency and the heat going through the enclosure, they're drying themselves out and maintaining that kind of longevity. As we insulate, as we get rid of the thermal bridges, we're making things airtight. We're closing down all those avenues for heat to move through the enclosure. The enclosure's getting colder. Colder things want to stay wet. And so the enclosure, as we increase the insulation levels, will want to stay wet longer. And we need to work harder to think about how to dry it out. And they're really only going to dry through vapor diffusion at the end of the day. So as we increase insulation levels, we're increasing moisture risk. We need to increase our drying reserves. We need to think about how we're going to be able to dry the enclosure out. And that's really where the rubber hits the road, so to speak. We need to assume that the building will get wet somehow at some point in time. Stuff happens, so you need a moisture-tolerant design. So we'd like the formula to have the drying capacity be greater than the unanticipated moisture stress. If we can maintain that relationship, then we have freedom from damage from this moisture damages to the enclosure. So stuff happens, help the drying. We're always thinking about helping the drying. Of course, we want to prevent the wetting, but we need, stuff is going to happen, we need to help the drying. We want to work with the dominant vapor drive, go with the flow, right? Much easier to go downriver than upriver. Why not work with that? In a cold and mixed climate, the dominant vapor drive is outward, and things want to be able to dry outward. We should let them dry outward, and this is true down to Washington, D.C., and again, North Carolina. You know, it goes quite far, this dominance of the outward drying. So from the inside, you know, we're looking to possibly have a vapor retarder. In the outside, we want to really encourage the drying. So the question we find ourselves asking is, why are we installing vapor dams around these buildings? You know, foil-faced polyiso is vapor closed. Nothing can dry outward. Now, it may be able to dry inward. This may work as an assembly. You know, there are a lot of different factors, and we'll be looking at more of them in a minute here. But really, they're not working with the flow here. They're making it dry in another direction. So how do we get to wrapping these buildings in polyiso and foam? Well, the exterior continuous insulation is addressing dew point. As we understand it, and it's in the code for some areas, if we have warm, humid air that's moving into the enclosure, so the interior is on the right side of this diagram, it's moving through the enclosure to the left. If we don't have continuous insulation outboard of that exterior sheathing will be cold. It will be the condensing surface. When that humid air hits it, it can condense, and we could have a mold problem in the wall. So we add continuous insulation outboard, and the question here is, how much insulation do we need to add to get that sheathing at a high enough temperature that we won't have a condensation risk? And what's happened over time is it's gone from continuous insulation to continuous foam insulation for any number of reasons, but that's sort of what the default is now in terms of that. But so foam is addressing this dew point issue in terms of building science. But the characteristic of foam is also problematic in that it's hydrophobic. It doesn't help the drying. It doesn't care about water. It's totally indifferent to it. And it can actually make wetness in that enclosure. So this is a diagram looking at sort of typical wall enclosures in Minnesota from the Building Science Corporation. And what we see is over the course of a year, looking at these different wall assemblies, and the red and orange ones are sort of typical 2x wall construction, and then the two blue ones have continuous, one with 1 inch of XPS and one with 4 inches of XPS. So pretty significant vapor retarders outboard as continuous insulation. And what we see at that sheathing then, at the inside face of that insulation, is over the course of the winter, it's becoming saturated in the course of, quite significantly in the course of the 1 inch of XPS. And then it's drying out again in the summertime, but then it's becoming saturated again. So we're dunking the building in water. And anytime we're above that line of 80% relative humidity, we have great concern about the possibility of increasing the risk. Now, if you're above and the temperature's cold enough, it's not an issue. But we definitely want to have concern about how long and how often we are going up so high. So it's making wetness, it's increasing risk, and as buildings get tighter and the interior relative humidities rise and we have more vapor drive into the enclosures, that risk only rises more. So foam, from our point of view, is making the enclosures more intolerant because as there's moisture, if there's leaks around windows, moisture getting in, it cannot readily dry outward. Sure, I'll try to refer to hot and humid as we go here. Yeah, Florida is a whole nother situation in a way. I'd be happy to follow up, Michelle, with you after. We could talk about that specifically. But I'll see if we can see what will apply here. So we want to reduce the intolerance and increase the resilience. That certainly applies everywhere. We'd like to see vapor open sheathing at the exterior. So just between when we get down to 1 and 2 in hot and humid, we're looking to be vapor retarding exterior and more vapor open interior, where above that typically we're looking to be vapor open outboard and vapor retarding, vapor variable inboard. So that's the big difference. As we've seen as far south as Gainesville, Florida, the vapor variability being very useful, but that's still pretty far north in Florida. Let me push on here. Vapor open sheathing at the exterior. Exterior grade gypboard is really excellent in terms of being vapor open. We also like to see no sheathing outboard. In this case, this is a house in Ohio where this OSB that we see on the left is actually inboard of the insulation layer. What happens is that insulation, which we see on the far right picture, is about 10 inches of dense packed fiberglass insulation, vapor open insulation, and that is wrapped in a WRB weather resistant fabric, waterproof, airtight, and vapor open. And so you're literally making a parka, sort of a vapor open parka around the house. Here we have a diagram of it on the left, where you see on the right of the diagram, it's basically a 2x4 stud wall with plywood or OSB. So you've basically got standard construction, and then you have an outrigger I-joist that's carrying the parka of the insulation with the vapor open membrane to the left enclosing that insulation, and then the siding outboard of that. And we'll come back around to this in a number of different ways here in a few minutes. I need to keep moving here, I think. We're also looking at back vented rain screens as being very good in promoting drying, very good in a number of ways in making a high performance enclosure. We like those vented gaps outboard of the insulation. We also wanted to look at the windows. So we've got back vented rain screen, which is helping a lot. We've got the vapor open sheathing or wrap. But then at windows, where we're most likely to have a leak, where we're most likely to have condensation, moisture problem, too often on the left we see traditionally sort of wide expanses of vapor closed material being wrapped around that's inhibiting the drying. We understand they're doing that for waterproofing purposes, but in the cases where we have water behind it, it's not able to get out. So we really want to think about the detailing and allowing the waterproofing to happen while keeping the enclosures as vapor open as possible. So for vapor retarding, inboard, we're looking inboard to do vapor retarding or vapor variable. We want to minimize the wetting of the enclosure from the inside. Now, vapor retarders inboard of the insulation could be required due to building code, depending on the precise situation, and this is way too much text and detail to get into, but just to say that to look at the different areas in the classes, and to also, in terms of, as we get into vapor retarders and barriers for that sake, that different materials have different permeabilities, and it's really important to get your mind wrapped around what those are, and at different thicknesses they may have different characteristics. So, you know, EPS could be vapor open, but at 3 inches of unfaced EPS it starts to get semi-impermeable. Aluminum foil obviously is vapor closed, and as we get to thinner pieces of EPS, it becomes semi-permeable, could be vapor open. Latex paint is often used as a vapor retarder. The big thing that we question is that it's not designed for it. There's no good data on it. There's nothing that gives one really sort of performance assurance in depending on that over time. So again, way too much information here, but just the importance is to look at the different materials in your assembly, look at the vapor profile, and how the things are going together. Vapor barriers, typically we say we want to just avoid completely, that we don't want vapor closed material in the assembly. Of course, roofs are often vapor barriers, an asphalt roof, an EPDM roof. So the last thing that we want is to have 2 vapor barriers in such an assembly. So no foil-faced insulation underneath a vapor-closed roof, because if you do have an air leak in, as this diagram shows, you could have potentially a swimming pool and a really sort of catastrophic damage, which has this sort of result, which is very much, they had a vapor-closed inboard and an air leak and big damages. What about the vapor permeable air barrier such as certain membranes? Does this class vary? Yes. So we'll be talking about the vapor variable materials momentarily. So I'll come back around to that. Well, right now we'll start to talk about it. Inboard vapor control material options. We're looking at natural materials can be vapor variable. Wood is vapor variable. So plywood and OSB can give you vapor variability. And then there are membranes that are manufactured to give you vapor variability. The vapor variable membranes of 0.8 to 5.5 or greater, that's in the range of the Certainties membrane and the Proclima DB+. And then we have quote-unquote intelligent membranes that have an even wider, have a wider range of variability. So what's nice about the vapor variability is that in the summertime, as the vapor drive is coming in, and we have vapor openness outside to the left here, the vapor variable material should allow the drying inward and will allow that enclosure to dry inward. So OSB is a vapor retarder, and we like to see it at inboard of the insulation. Again, it's kind of funny because we think of OSB and plywood as typically being outboard sheathing of buildings, but we actually, because of their vapor retarding properties, prefer not to see them out there. But inboard, yes. So here on the left, again, we have this idea of the parka, where that OSB is actually inboard of the insulation. Here's some models from our office illustrating this with plywood. Here we have the membranes with greater permeability range, so 0.8 to 5.5, and then the widest range possible is 0.17 to 13.2 and above. And really, generally, basically what we're looking at is based on the vapor, based on the moisture risk that we see in the enclosures, you know, depends on how aggressive we want to be in approaching this. So the intelligent vapor retarders, they don't know what time of year it is. They don't know there's no sort of magic to it. They're just like wood, opening and closing based on the humidity around them. When something's dry, like wood, it will close and it will be more vapor closed, and when it's more moist, it opens and becomes more vapor open. These materials are just designed very specifically to have vapor curves that increase the robustness. So in the wintertime, it's preventing wetting. In the summertime, it's allowing drying. So here is the vapor curve of one of the membranes. What we see is that in the wintertime, it's very vapor closed. And then as it gets towards a high humidity level, again, it starts to open up dramatically. Again, we have that 80% line we don't want to cross. So as it approaches 70%, it really starts to open and then opens wide to allow drying outward. As an illustration here, what we see is on the left, the wintertime, the vapor drive is going out, upward. We have about 50% relative humidity inside the membrane, about 30% outside, because if there's any moisture in that assembly, it's pushing to get outward. So the membrane's at the driest point. So we have an average humidity of about 40%. It's retarding. In the summertime, the vapor drive's coming in on the right here. We have about 90% relative humidity within the enclosure. That membrane is now at the wettest part of the enclosure. If there's any moisture in that enclosure, it wants to get in. It's up against the membrane. It's kind of the canary in the coal mine, if you will. We have relatively high inboard relative humidity in this case, interior. And so we have an 80% average, and it's going to be wide open and allow the drying inward. So with that, it really builds the drying reserves. Now, there is no guarantee against moisture protection. There are all kinds of things vying to wetten the enclosure. We have diffusion, again, which is always uppermost on people's minds, but is relatively not that important in terms of wetting, although we certainly try to prevent it. Wet construction introduces a lot of moisture. We also have flank diffusion, where you may have masonry construction, carrying moisture around your vapor retarders. And then, again, the air leak, which is the disaster, which carries geometrically more moisture into the enclosure. So what we see is we have moisture-loaded job sites often from the weather, from the materials, and they need to dry out. And cycling over the years through the seasons, what we can see often is with the intelligent membranes, it really allows those enclosures to cycle through and become safe and stable. So in terms of the brand names, let me just run through these really quickly. I think warm climates vapor retarders are installed on both indoor and outdoor sides of cavities. It depends on the characteristics. Again, when we get into tricky the climates, you know, we can actually run in our office WFI simulations, dynamic moisture simulations of the enclosures to see what the different material characteristics will do over time. It's no guarantee in terms of performance, but we can tell if one approach is relatively riskier than another or relatively safer than another, and see what steps we can take to make things safer or more risky, depending on comfort levels. But often we see in warm climates, we do see what we would see vapor retarders outboard in hot and humid. We're talking about climate zone 1, and probably still the vapor variable inboard would work. We wouldn't want the vapor variable outboard in the hot and humid though, because when it gets this hot and humid, it's just going to allow it to dump inward. the name brands of the intelligent membranes is really, so membrane is one level of it from Certainteed, and then we have from Proclima, on our website, it's called Intello Plus by Proclima. So you should look at both of those, are the leading brands. So even with unvented roof, this is too complicated to explain right now, but it shows that blue line, the green, the black, and the red lines show different levels of distress, and the blue line shows with the intelligent membrane with the moisture levels diving down. So it's relative, but I don't want to go into all of this now. So we have the intelligent membranes really helping in all sorts of situations help build drying reserves. Even in masonry retrofits, I'm going to just jump over this because time is getting tight, but we have actually a whole other talk which may be of interest on high-performance historic masonry retrofits and what we can do to make them, if not passive house, close to passive house level, and make sure we're protecting them for the long term and not damaging the masonry construction in the process. So drying in and out, similar principles in masonry. Looking at insulation, we said the foam was hygrophobic. We like insulations like cellulose, dense packed cellulose in particular, which are hygroscopic. So rather than ignoring the water, it actually helps manage the moisture. The cellulose takes the moisture from a wetter area and moves it to a drier area and increases the drying capabilities of the enclosure. So that's very positive. We like to see thermal bridge free construction. So we're talking about the continuous insulation. There are a number of ways to approach thermal bridge free, whether it's continuous outboard insulation, double stud construction, the I-joist outrigger, lots of different things we can get into. We also like mineral wool or wood fiberboard insulation. The mineral wool is great in that it's fireproof, and so rather than wrapping your building in a fire accelerant, you're actually wrapping it in a fireproof material. It's vapor open, the wood fiberboard as well. So we're eliminating thermal bridges through that. We also look at, and I won't dive into this here, but the sort of slab on grade is the final frontier. We're heartened that Roxol has recently approved their IS board to be sub-slab on grade, so we don't need to necessarily use foam boards for that. And we're also looking at inverting, so we put the slab on the grade and we put the insulation on the slab as a way forward.
Is that, Ken, is that Roxol or rock wool only for slab on grade, or does that work in basement situations too?
Yeah, no, you wrap your whole building in it. All sorts of different applications for it, definitely in basements, in the walls and roofs. We were seeing the Roxol used off-label, if you will, a sub-slab, because it seemed to, per the specs, it seemed to have the carrying capacity. And then finally, after a few years of folks talking about it, they finally released some information officially blessing that application for it. Any experience of dense packed cellulose settling and creating voids? So definitely one of the issues with the dense packed cellulose is, with any of this stuff with high performance is we need proper installation. One of the things that we look at, and I don't know if I have, we use, if I could use an image here, well, if we use, let me see this one. So this image where we have the this black membrane on the outside, which is the WRB, it's Mento Plus membrane, and that's the parka. So you're dense packing behind that membrane. And what's nice about dense packing behind the membranes is that you can feel them. You can feel where it is and where it isn't. which is really critical in having a good job. And on the inside, if you can use your interior membrane as the dense packing material as well, you can actually see the material through it, you can feel it, and you can see where it is or isn't. And if you're hitting the densities specified, you should not have settling issues. It will last and maintain the complete coverage. It's when there are voids at the installation, the density is not reached at the installation, things like that where you don't have the quality control up front where you could run into problems. But certainly they're very avoidable and detectable, which we'll speak about in a second here. So let me jump back ahead. Roxel subslab. So we want to make it so really quickly here. I know I'm running out of time, but we'll get through this. We want to make these control layers predictable and durable. This is how we're going to, have this high performance. And the predictability and the durability is really dependent on the continuity. Continuity at the end of the day is the real buzzword. And so what we want to do is look at, in particular, all the junctures really carefully in a building where things come together, and the penetrations where things are going through the control layers. We want to look at the robustness of the materials, simplify things, sequencing. We want to verify things, repair them, and protect them. So we'll quickly run through this here. And this is in contrast. We like to point to continuity in contrast with discontinuity. And if we're relying on spray foam in between studs to have our airtightness layer, we have joints in our airtightness and vapor control layer, more often than every 16 inches on center. They're everywhere. They're going. And, they're all potential failure points. It's also very hard to tell sometimes, certainly visually, whether you've got airtightness or not, which in the top middle, we like to say at a window install, feel free to use the can of foam for thermal insulation around the window if you must. If you want to, that's fine, but don't rely on it for airtightness. You still need to tape that connection and get airtightness, because even if you have a perfectly looking foam job, you put a blower door on it, you're going to see air leaks around. So there's all sorts of issues in terms of discontinuity, and we want to nip those and make sure we maintain the continuity. So we want to seal the entire envelope. We want to think of all the components in that envelope as parts of this continuous effort. And in thinking about how to do airtightness in particular, airtight drywall was sort of grown up as a way to do it, and understandably so. It's airtight material in and of itself. It's going around the exterior of the building, but there's huge problems with it. If you really want performance and long-lasting performance, we consider drywall a sacrificial layer. It's going to get beat up, ripped into. It's also the joints are going to crack over time, and it's not continuous. It stops and starts all over the place. So it really has some big hurdles built into the approach, so we recommend against that. Sheathing, we like. Again, we don't like the vapor retarding properties on outboard in the cold and mixed climates, but inboard it's great, and it's really robust material. It takes a beating, and it acts as a Class 2 vapor retarder. So not that typical, but certainly appropriate. Weather resistant barriers, basically we have a new generation. The old typical house wraps have micro tears in them to allow the permeability. They leak. They may meet the definition of an airtight material, but they actually provide too much leakage that you can't get to really high tightness levels with them. But there are new materials out there that are truly airtight, truly waterproof, a 33-foot water column, and that are vapor open. The vapor moves through at a molecular level, not through micro tears, and gives you really more robust. Adhesive tapes are also very important. They have a wide range of quality, so it's very important to look into those. The connections, the robustness of the connections are very important. Traditionally, the sealants will brittle and fail over time, but with the new approach, with pressure-activated adhesives, with fabrics, we can make these connections, the buildings can move, and we can maintain those connections, which are essential to the continuity. We want to bring together dissimilar materials that will maintain the continuity, porosity, unevenness, those sorts of things. Foam is not optimal and it's not reversible. What we see is that high performance is going to the factory in terms of making higher quality and quality control. And with spray foam, we see it going in the opposite direction. We see them bringing manufacturing onto the job site, manufacturing in poor conditions with construction workers, with many factors around it, and we see it compromising the quality of the work. We want to simplify the details. We want to have the continuity going through. Simplifying the details is a big leg up in terms of maintaining what's possible. We want to sequence things properly. Here we see an image of a piece of membrane put up, and then on the right, a wall perpendicularly framed into it. By doing this, they've maintained the continuity in a very simple way in the sequencing. They could have done the airtightness after it, but it would have been a very complicated joint to go around. Wire and pipe penetrations are big points of discontinuity and where things can fall apart over time. There are EPDM gaskets, there are tapes, there are ways of doing this. We like to compare it to penetrations through a roof, where we want to maintain space between the thing and the walls around it so that you can get to it, you can find the leak, you can fix it. Joists, window penetrations, there are many ways of approaching it. We can look from the inside, from the outside, different tapes. Window penetration, ceiling, here we have a window box going through what will be the insulation layer and the connection. You see on the upper right a detail with the outboard and inboard control layers identified. We have many, many details like this that you can download. We want to be able to apply the materials on typical job site conditions. It gets cold, it gets wet. There are materials now that have greater moisture tolerance and greater temperature tolerance than the traditional materials. And we want to verify airtightness, even if we're not going for a specific number, even if it's not for Passive House or a specific certification program. We recommend putting a fan on the building. Even if it's not a technical blower door and you're not measuring it, just pressurize it and depressurize it. Feel the air leaks, go around, make it more airtight while you have the chance. The airtightness of that enclosure, while you can get to it, while you can do it, will have a huge effect on the performance of the building going forward. And so we want to take that opportunity. Of course, it's great to measure it, and it's great for the team in terms of finding the air leaks and making it higher and higher performing. It really changes the way the team looks at the building. It's not like arguing over paint quality or finish of a stone. It's something they can feel, something they can fix, and really take pride in the performance of doing it. Yep, when you get really tight, you can just use duct blasters. It's quite amazing what's possible today. Key thing is to have things be repairable. So we're getting tighter and tighter and tighter. With foam, we see the reversibility, the repairability as being a real hindrance to getting to real airtight levels. If you're trying to do a passive house, you cannot rely on spray foam to do it. It just will not get you to that level. Finally, we want to protect the control layers. We've tested, we've repaired. Now we want to enclose them and protect them. Again, a vented rain screen on the outside is really a great tool for having high performance. And inside, the service cavity is a new thing that we're trying to make more common in the U.S. market, and we're seeing greater and greater acceptance of it in that it's rather simple in applying the strapping inboard of the air barrier, and by having this service cavity, we're eliminating all of the holes through the control layers for light switches and electrical boxes and such, and really limiting them to just the windows and the doors and the services. As we can eliminate penetrations, we're increasing the likelihood of better performance. And that's really it. To summarize, we want these control layers to be continuous. This is going to be the driving thing. We want to have excellent materials, and as the insulation levels rise and the risks associated with higher insulation levels rise, we want to be more and more aggressive in terms of controlling the vapor control, and certainly smart vapor retarders can help a great deal in minimizing risk. To the extent that we can minimize or eliminate the use of foams, we can really have higher performance and more sustainable, more healthy building. We always want to blower door the buildings. We want to protect the control layers, and we want to help you do it. So thank you very much for this. I'm happy to stick around and answer more questions, and certainly can follow up offline. Again, we have lots of resources, and we hope you take advantage of them. Thank you for having me.
Hey, Ken, great. Thanks. This is great. This is a lot. For those of you who are still sticking around, I know there's some questions that have piled up. We have some time for some more questions. Your surveys should be on the way there. And definitely when you're taking that, we'd love to hear from you on maybe some more specifics that you'd like to drill down into. If we did another session like that, we'd really appreciate that feedback, because there was a lot of questions on some more things that you wanted to see covered. And that's kind of a question to everyone in the audience here. For those of you, also real quick, again, in that survey, take that to get your AIA CEUs, your certificates being sent to you. For those of you listening on demand, stick around still for the questions, but you'll get a quiz that you'll need to take and complete that quiz after this session. So Ken, it looks like we've got kind of several questions about these topics on mixed climates and hotter climates. Do you think that could maybe even be a whole other session in itself? Maybe, or you could quickly, briefly address, that as an overview?
Sure. I mean, just again, the basic issue is what we need to look at. It's very climate specific as we move from the mixed climates to hot and humid in particular. What the vapor dynamics are moving through the enclosure. Generally speaking, what we're moving when we are in truly hot and humid, we're looking at vapor retarding outboard, airtight outboard. So we're keeping the hot and humid air of the environment out of the insulated enclosure again, because now we're pretty much over air conditioning these buildings, right? We've got essentially a refrigerator going. in a hot and humid environment. So that risk, that moisture risk in the enclosure is flipped. Inboard, it still may make sense to do a vapor variable membrane or just have it be vapor open inboard. And again, running WUFI simulations on different assemblies will help determine, what the risk range is. Again, they won't necessarily say, well, this will fail or this will work, and sometimes, but 100%, but it could give you a relative sense of safety or risk. So that's the general thing. Of course, ventilation is hugely important, and doing energy recovery, moisture recovery in the ventilation system can help a lot in the hot and humid climates to keep the dry air inside, so you can minimize the dehumidification requirements. You probably still have to dehumidify, but hopefully you have to air condition much less to just dehumidify. The idea would be to have a really tight, high performance enclosure. There's a question about, well, whether passive house or airtight enclosures, belong in hot and humid climates. But the fact is, well, they do belong is the short answer. And the fact is that keeping that hot, these buildings' energy uses are driven by dehumidification because they've got leaks and they've got all this hot and humid air moving through the building that they're trying to dehumidify. So by keeping that hot and humid air out, you're driving down those energy loads requirements and maintaining a much more controlled environment, better environment.
Great. Getting into insulation a little bit, do you have any concern about the ability of these fabrics to hold cellulose over many years, 50, 100?
No, not at all. I mean, it's important, again, that the installation is done correctly, and there are certainly installation guidelines in terms of spacing of supports and battens and all of that. But the materials are well tested, and we do take heart that the adhesive tapes are one of the big new technologies, which it's not so new. The tapes have come out of the aerospace industry over the last couple of decades, but there are some specific attributes to them that are more refined. We have, for example, the tape's been advanced age tested now beyond 100 years.
Yeah.
So the we take heart that the Germans, build their buildings to last 100 years. They don't build them to last 20 years, like might often be done on this side of the ocean. So that in and of itself isn't a guarantee, but definitely the components and the quality of the materials are put together in a way to have buildings that will last generations.
Keeping on the insulation topic, what are your thoughts in regards to the foam being used in structural systems like SIPs or ICFs?
Sure. I mean, so there's a big, so spray foam is like the boogeyman, is the worst of the worst. The closed cell spray foam is the worst, and then you have open cell spray foam. Open cell spray foam is only better in terms of the blowing agent. In the closed cell, they're changing the blowing agent, so that may not even be such a big deal anymore, but all the really toxic chemicals that are in the closed cell are in the open cell, and the real issue with that, again, is that the manufacturing is done on the job site. And so, these construction workers are in hazmat suits with full respirators, not because it's a green, sustainable material they're working with, because it's absolutely toxic, horrible stuff. The EPS, the foam boards, are a huge step in the right direction. And what they're doing is taking that manufacturing and putting it in the factory where it belongs, and doing it under controlled environments. So you're much more likely to have what the spec says. You should be getting it when it's in the factory and they're doing quality control testing, where in the job site, spray foam is, it's sort of the Wild West. So in that respect, it's good. It's a big step in the right direction. Ultimately, though, we're just looking in our environment today to detoxify as much as we can. We're surrounded by plastic. Plastic isn't going away. The materials we all work with and deal with are, dependent on plastic in one way or another, but we're looking for ways to minimize it. And we can have building insulation that absolutely minimizes the use of plastic foam insulation or eliminates it altogether, which we think is, another step in the right direction. So the SIPs, in terms of the foam plastic, it's definitely, it's much better than spray foam. We also, regarding SIPs and foams, there's a whole other discussion about, just the long-term performance of that and what the tolerances are and what we want to be looking at to make sure that we've got longevity in the performance. But yeah, I hope that's somewhat coherent.
Yeah. What another question, kind of referencing probably more smaller urban homes that are being built in limited space and probably still using 2x4 wall construction. What are some of your recommendations for those types of projects?
Right. Well, we would still recommend using fiberglass, cellulose, or mineral wool or wood fiber. We would prefer to take the hit on the R value and make up for it in the airtightness. The airtightness will drive the performance of the enclosure to a much greater extent than an inch or two or an R value or two will get you out of the insulation. When we look at the energy models for buildings, if you can drive the airtightness of the building, you can actually eliminate inches of insulation and to achieve the same results. So focusing on the airtightness is really the top priority, and worrying about the thickness of the insulation is secondary in our opinion.
Thanks.
I could add to that, the other thing that's also more important than just the pure inches or the pure R value of the insulation is the continuity of it. So, give up an R to have, wood fiber or mineral wool or fiberglass or cellulose, but along with airtightness, the other key thing is thermal bridge-free construction. And I know there was a question I think about that, and just really, thermal bridges are where there's discontinuity in the insulation and you have disproportionate amount of energy moving through it. If you can detail and build out or minimize the thermal bridging, you will just have an outsized impact on the overall performance and health of the building.
Great, thanks. And then there's gonna be I believe, we could probably have a whole session on retrofits. It sounds like there's a lot to be discussed there. But there are some, even whether new construction or existing here, especially in the Midwest with, the rim band joists, and that's always a tough spot to get into and
Yep.
air seal without foam. What, any quick recommendations on that?
Yeah, it might be the final frontier of foam. We would like to see going in and using a combination of membranes and tapes, and we've certainly seen it done in liquid membranes. There, different combinations of systems. In the historic masonry retrofits where we have joist penetrations into party walls and literally hundreds and hundreds, typically we're seeing a combination of liquid membranes and tapes making it all work. But yeah, when you're looking at a band joist going around, oftentimes we've seen many jobs where they're using membranes for the walls and the roofs, and at those band joists is the one spot where they're using spray foam.
I know for my mother's existing house, we did
Yeah.
sort of a can of great stuff, you know, in the edges there, and then just we have actually a locally made rigid cellulose, and just cut that out and fit it right in there, and it seemed to work pretty good. But
Cool.
have you ever seen that Eco Seal stuff from Knopf? It almost seems like that could be a good application for the existing ridges, or the
absolutely.
The joints. Yeah.
Absolutely.
But
we like to, on the existing, what we prefer to see is going from the outside, you know, taking off the siding, basically wrapping the building like a Christmas present with new house wrap that, you know, is waterproof, airtight, and preferably vapor variable, and then putting continuous insulation, strapping, siding, and, you know, moving the windows out. Substantial work, to be sure, but has its applications.
All right, Ken. Well, that's about all the time we have for questions, but I'd definitely like to invite you back to do some more sessions and topics with us. I think there's a lot to cover. If you're interested, there's a lot of great comments and questions out there. Real quick, yeah, where can people get where can they contact you for more information if they want to reach out?
Yeah, please. Our website is 475.com, and that's spelled out FOURSEVENFIVE.com. My email is ken@475.com, and please drop us a line. Happy to take a look at drawings. We like to look at details, try to help optimize things, and figure them out.
Great. Well, thanks, Ken Levinson, for your time today. We're going to get wrapped up. Yeah.
Thank you, Brent. Thanks, everybody.
Yep. This has been another session from the Green Home Institute. Stick around on demand online to learn more and get plugged in. Have a great week, everyone. Thank you.
You too.